Glass. It's everywhere. In your windows, your wine glasses, your car windshield, and even the phone you're probably holding right now. But here's the question. Have you ever stopped to wonder where glass actually comes from? I mean, is it mined, grown, cooked up in some chemistry lab? What if I told you it all starts with sand? Yep, that fine grainy stuff you shake out of your shoes after a beach trip. Today, we're going behind the scenes to uncover how something so ordinary becomes something so extraordinary in a high-tech factory where science meets heat and raw nature becomes sleek, clear, and ready for the world. So let's start at the beginning, with sand. But not just any sand. We're talking high-purity silica sand, the good stuff. Factories get this special sand from carefully selected quarries, and it has to be squeaky clean. No dirt, no weird minerals, no shells. Just fine, pure silica. It's the backbone of glass. But here's the twist. Sand doesn't work alone. It needs a few co-stars. Soda ash helps the sand melt more easily. Limestone makes the final glass stronger and more durable. Cullet, which is just a fancy word for crushed up recycled glass, helps everything melt faster and uses way less energy. All of this gets delivered in bulk, by truck, train, or even ship, and stored in giant silos. Think of it like a massive pantry for a very hot recipe. Now that we've got our ingredients, it's time to mix the perfect batch. Modern factories don't leave this to guesswork. Everything is done by computer, weighing each ingredient to the gram. Think of it like baking, but on a giant industrial scale. And instead of cookies, you're making windows. Conveyor belts carry the sand, soda, limestone, and cullet into a giant blender called a batch mixer. This machine tumbles everything together so that the mixture is perfectly uniform. In some facilities, they even preheat the mix using leftover heat from the furnace. It's like preheating your oven, but also saving energy in the process. Smart, right? Alright, time to crank up the heat. Literally. The mix heads into a glass melting furnace where temperatures reach a blistering 1500 degrees Celsius. That's over 2700 degrees Fahrenheit. Hotter than lava. Seriously. Inside the furnace, the sand and its companions melt into a glowing orange liquid river. Thick, sticky, and mesmerizing. But this isn't instant soup. It takes time. Up to 24 hours of slow, even heat to get that perfect glass consistency. Factories use sensors and cameras to monitor everything, adjusting the heat, checking the flow, and making sure the glass is as smooth as honey and free of bubbles. Because nobody wants lumpy glass. It's like alchemy meets engineering. Now comes the fun part. Depending on what kind of glass you're making, the shaping process looks totally different. Let's look at the big three. Flat glass. For flat glass, the factory uses something called the float process. Here's how it works. The molten glass flows onto a bed of liquid tin. Yes, real molten tin, because glass floats on it like oil on water. The glass spreads out into a smooth, flat sheet as it glides across the tin. It's kind of like watching pancake batter settle, but glowing hot and way more precise. The sheet cools just enough to hold its shape and then rolls forward like a glowing ribbon. Perfectly flat, perfectly smooth. Bottles and jars. If the factory is making bottles or jars, the molten glass is sliced into gobs, like little dollops of honey. These gobs drop into metal molds, then compressed with air or pressure in 2 steps, first shaping the neck, then the full bottle. This process, called blow and blow or press and blow, is shockingly fast. We're talking 600 bottles per minute, flying down the line like magic. Glass fibers. For insulation or fiberglass, the molten glass is drawn through tiny holes, like pasta through a spaghetti maker, creating thin, hair-like threads. It's fast, hot, and incredibly delicate. and the result is strong, light fibers used in everything from walls to boats. Once the glass is shaped, you can't just let it sit out and cool. That's a recipe for cracks and disaster. So it goes into something called a layer. Basically a long, slow-moving oven. Here the glass cools down gradually, in a controlled environment. This process is called annealing, and it relieves internal stresses that could make the glass shatter down the line. Whether it's a giant window or a little olive jar, annealing is key to durability. And this tunnel isn't short. Some layers are over 100 feet long. Now that the glass is cool and stable, it's time for the finishing touches. Flat glass is cut to size using diamond wheels. Yes, real diamonds. It's the only thing hard enough to score the surface cleanly. Then the edges are smoothed and polished for safety. Some sheets are even coated with thin layers of silver or other metals to create mirrors or solar glass. As for bottles, machines check everything: symmetry, thickness, strength. Every bottle, every jar, every panel is inspected by lasers, sensors, and high-speed cameras. Some lines even use AI to detect the tiniest defects. What doesn't pass inspection? Back it goes to the furnace as cullet to try again. Nothing is wasted. Depending on what the glass will be used for, it might get a few more upgrades. Want stronger glass? Enter tempering. Tempered glass is reheated, then cooled super fast with blasts of air. This makes it 4 to 5 times stronger than regular glass. And if it breaks, it shatters into small, blunt pieces. Much safer. Or maybe you want glass that holds together on impact. That's laminated glass, with a clear plastic layer sandwiched between two sheets. It's what keeps your windshield from exploding during a fender bender. And then there's smart glass coatings, like low-E layers that reflect heat but let light through. Perfect for keeping your house cool and your AC bill low. Finally, the finished glass is ready to leave the factory, but it has to be packed just right. Flat panels are stacked with soft pads in between. Bottles are grouped into neat packs and wrapped tight. Fiberglass is rolled or boxed depending on use. Robotic arms lift and stack everything onto pallets. Forklifts roll in, trucks roll out. Some of this glass will travel across the state. Some will cross oceans. From your local grocery store to downtown skyscrapers in New York or Shanghai, it all started with a grain of sand. Here's the cool part. Glass is infinitely recyclable. You can melt it down and remake it again and again, without losing quality. Modern glass factories are going green in a big way, using more cullet cuts, energy use and emissions. Electric furnaces are replacing gas ones. Solar panels, waste heat recovery, and closed-loop water systems are all becoming standard. Some plants even run on 100% renewable electricity, turning the ancient art of glassmaking into a beacon of sustainable innovation. If you enjoyed this deep dive into how ordinary sand becomes the glass all around us, imagine what else we've got coming. We're just getting started. So don't miss out. Hit that subscribe button, give us a thumbs up if you learned something new, and drop a comment telling us what process you want to see next. Small, fast, and deadly accurate, a bullet is one of the most precisely engineered pieces of hardware on Earth. Behind every round lies a combination of chemistry, metallurgy, and engineering, all executed under tightly controlled conditions where even a microscopic flaw could mean failure. In this video, we go inside one of the most secure and advanced ammunition manufacturing facilities on the planet to uncover the step-by-step process of creating a modern bullet. From raw materials to final packaging, from sheets of brass and powdered chemicals to high-speed robotics and rigorous ballistic testing, you're about to discover how firepower is forged with surgical precision. This is not just about metal and machinery, it's about safety, control, and trust. Because when a bullet is fired, there's no second chance. Coming up, what materials go into a bullet and why each component is critical to performance. Before any bullet is assembled, it begins as a collection of raw materials, each selected with scientific precision for its role in creating power, control, and reliability. At the heart of every cartridge is the casing, typically made from brass. This golden-hued alloy of copper and zinc is prized not just for its durability and corrosion resistance, but for its ability to expand and contract predictably under pressure. When a bullet is fired, the brass casing expands tightly against the chamber walls, forming a perfect seal to prevent gas leakage, then cools and contracts, allowing it to be ejected cleanly. Massive rolls of brass sheet arrive at the factory, inspected for microscopic flaws before being fed into forming machines. But the casing is only the beginning. At its base lies the primer, a small metal cup containing an explosive compound that is sensitive to impact. When struck by a firing pin, this tiny component ignites instantly, creating the initial spark needed to activate the propellant. Because of its volatility, primer manufacturing takes place in specialized environments, often under robotic control to ensure maximum safety. Workers in this section wear anti-static suits, and the process is monitored with precision cameras to detect even the slightest error. Once the primer does its job, the fire moves to the propellant, a refined chemical mixture packed tightly into the casing. Today's bullets no longer use traditional black powder. Instead, they rely on modern smokeless powder, typically made from nitrocellulose and various stabilizers. This powder burns cleanly, reducing smoke and residue, and can be tailored for specific ballistic profiles. Every grain of powder is measured with incredible accuracy, because even a slight deviation could alter performance or, in extreme cases, cause catastrophic failure. Finally, there's the projectile. The bullet itself. Usually, it starts as a lead core for weight and density, then gets wrapped in a copper or brass jacket to increase durability, reduce fouling, and enhance aerodynamic stability. These jackets are drawn from copper sheets, shaped with high pressure, and bonded tightly to the lead inside. Depending on the intended use, bullets might be shaped for expansion, penetration, or accuracy, ranging from full metal jackets to hollow points and even armor-piercing variants. Regardless of the design, they all share a common goal: delivering force with precision. Each of these components, brass, primer, powder, and projectile, is engineered independently, but they must work in perfect harmony. Together, they form the anatomy of a modern bullet: a miniature explosion chamber, a propulsion system, and a precision-guided point of impact. The journey of a bullet begins with a simple disc of brass, cold, flat, and unassuming. But in the factory, this raw material is transformed into a critical component through a process that requires extreme force, heat, and precision. The first step is known as cupping, where brass sheets are punched into small circular blanks. These blanks are then pressed into shallow cups through a powerful drawing machine. From here, the cups undergo multiple stages of drawing and annealing, a process that gradually stretches the brass into long, narrow cylinders while carefully applying heat to prevent cracking. Annealing softens the metal just enough to keep it ductile, flexible but strong. Each casing is trimmed to exact length and passed through a washing station that removes residue and oils. They emerge clean, golden, and perfectly smooth. But they're far from finished. At this stage, each casing is run through a series of progressive dies that shape the neck and mouth, form the base, and create the primer pocket with tight tolerances measured in microns. To ensure reliability, every casing is subjected to automated visual inspection. High-speed cameras check for dents, deformities, and thickness irregularities, rejecting any imperfection without hesitation. Only flawless cases move forward. Despite the rapid pace of production, the standards remain unforgiving. A single crack or off-center primer pocket can lead to failure in the field, something no soldier, officer, or sport shooter can afford. By the end of the process, that thin piece of brass has become a highly engineered pressure vessel, strong enough to contain an explosion, yet light enough for rapid cycling in modern firearms. While the casing forms the body of the cartridge, the projectile, commonly called the bullet, is the part that truly defines its purpose. It's the piece that flies downrange, pierces targets, and delivers impact. Crafting it requires a delicate balance of weight, shape, and durability, all shaped through fire, pressure, and science. The core of most bullets begins with lead, prized for its density and malleability. Solid lead ingots are fed into industrial furnaces, where they're melted down into liquid form. This molten metal is then poured into molds or extruded into long wires, which are later cut into small cylindrical pieces, each precisely measured by weight. These lead slugs will become the heart of the bullet, but a soft lead core on its own wouldn't survive the velocity or friction of modern firearms. That's where the jacket comes in, a thin layer of harder metal, usually copper or a copper alloy, designed to encase the lead and protect it during its journey through the barrel. Sheets of copper are cut into discs and drawn through a series of dies, forming cup-like shells that will wrap around the lead cores. Once the jacket and core are prepared, the two are pressed together in a process called swaging. Under massive hydraulic pressure, the lead fills the jacket cavity, and the entire assembly is reshaped into its final aerodynamic form. At this stage, the bullet's nose profile, weight, and dimensions are carefully controlled to match its specific purpose, whether it's for target practice, hunting, law enforcement, or military use. Different designs call for different levels of complexity. A full metal jacket, FMJ, offers smooth feeding and deep penetration, while hollow points are engineered to expand upon impact, increasing stopping power. Armor-piercing bullets may incorporate hardened steel or tungsten cores, offering enhanced penetration for specialized missions. Every bullet must be nearly perfect. Even the slightest deviation in weight or symmetry can affect accuracy. That's why each batch is spot-checked using digital scales, micrometers, and profile gauges. Precision is paramount. By the time the process is complete, what began as soft lead and flat copper has been transformed into a high-speed projectile capable of withstanding extreme pressure, rapid acceleration, and precise trajectory, all in a fraction of a second. Now that the brass casing has been precision-formed and the projectile expertly shaped, it's time for the most critical stage of all: assembly. This is where the bullet becomes a complete cartridge, a self-contained unit of power, accuracy, and engineering excellence. The process begins with the primer. These tiny but essential components arrive from a separate, secure part of the facility where they've been manufactured under tightly controlled conditions. In the assembly line, robotic arms carefully insert each primer into the casing's base. The fit must be snug, tight enough to hold during recoil, yet precise enough to detonate reliably when struck by a firing pin. Next comes the propellant, a precisely measured dose of smokeless powder. Automated powder dispensers ensure that each casing receives the exact amount required, down to the grain. Too little, and the bullet might not leave the barrel. Too much, and it could cause dangerous overpressure. The powder is funneled into the casing and leveled using vibration and air jets to ensure consistency. Then the projectile, the bullet itself, is seated into the open mouth of the casing. This step demands millimeter-perfect accuracy. The bullet must be pressed to the correct depth and aligned with the casing's axis. A process known as crimping follows, where the casing mouth is slightly rolled or pressed inward to lock the bullet in place. This not only secures the bullet during handling and transport, but also helps control pressure when the cartridge is fired. Throughout this stage, sensors and cameras monitor every step. Machines verify seating depth, crimp tension, and powder levels using real-time imaging and weight checks. If any cartridge falls outside of the strict tolerances, it's automatically rejected and flagged for inspection. The speed is staggering. Modern facilities can assemble thousands of rounds per hour. But despite the volume, quality is never compromised. Each machine is calibrated daily. Operators inspect samples from every batch, measuring bullet runout, neck tension, and even chamber pressure using advanced diagnostic tools. Different calibers, such as 9mm, 5.56 NATO, or .308 Winchester, require unique adjustments to tooling and timing. The machinery adapts quickly, thanks to computerized control systems that store profiles for each ammunition type. By the end of the assembly line, what started as separate components, brass, primer, powder, and bullet, has become a powerful, precision-engineered cartridge, ready for use in everything from sport shooting to military operations. Each round is identical in weight, shape, and performance. It's not just ammunition, it's consistency made real, one round at a time. Before any bullet reaches the market, it must pass a series of rigorous quality checks. In an industry where precision can mean the difference between success and failure, every round is scrutinized for perfection. Automated systems, equipped with high-speed cameras and laser sensors, scan each cartridge for defects, checking bullet alignment, primer depth, casing length, and overall dimensions.